Welcome, everybody. My name is Kevin Jernigan. I am a Principal Solutions Architect for the Aurora Postgres product. Today with me, I have Steve Abraham, who's Principal Solutions Architect for Aurora MySQL.
My name's Steve Abraham. I'm a Principal Database Architect with the Amazon Aurora Service Team.
Today, we're going to talk about how to optimize your business continuity strategy with Amazon Aurora Global Database. But let's start with a short background on Amazon Aurora. Aurora is an enterprise database at an open source price point that's delivered as a managed service by AWS. We designed it to deliver the speed and availability of high-end commercial databases with the simplicity and cost effectiveness, the cost profile of open source databases. It's drop-in compatible with both MySQL and Postgres, and has a very simple pay-as-you-go pricing model, all of this delivered as a managed service. So we'll start by talking a little bit about Aurora's architecture. But first, we really need to talk about how databases have been designed and built for the last 40 years. And they're all about I/O. And what you can see on this slide is a simple picture of a database. You have a compute node with query processing and transaction manager and buffer cache and redo logging connected to attached storage with hopefully very high bandwidth connection. And for 40 years, the fundamental design principles for this architecture haven't changed. Increase the I/O bandwidth between the database and the storage, and decrease the number of I/Os. And as long as you were able to do both of these things, your database would perform well, and you could continue to improve on the performance of database. In the cloud, however, we have a different imperative. The compute and storage have very different lifetimes. The cloud provides elasticity with instances, which means that customers operate in a very different way than they do on premises. Instances fail and might be replaced. Instances will be shut down to reduce costs. Customers will scale up or down the instances based upon workload. And instances are added to a cluster to scale out. So, based on this, we strongly believe that in the cloud, compute and storage have to be decoupled to deliver the best scalability and availability and durability. And that means that storage moves to the network, which means that the pipe between compute and storage is no longer that fat pipe, it's more of a thin pipe. And what that really means is now that the pipe between compute and storage is relatively thin, the I/O bottleneck has moved to the network. Now, Aurora is a database service that we have built to address this fundamental bottleneck in the network. We offload redo log processing to storage in Aurora, and we have two tiers, a database tier that looks like a traditional database, and a storage tier which looks very different than any storage system which has been built for databases. The database tier in Aurora writes redo log records on the network using a 4 out of 6 quorum protocol to the different nodes in the storage tier. Apart from these redo records, which can be thought of as change vectors or deltas for changes to the data blocks, nothing else is written. There are no full data blocks written whatsoever, not for checkpointing, not for cache eviction, not for background writes. Instead, the log application, which we've had in databases for 40 years, has instead been moved to the storage system. The storage system itself is a highly parallel scale-out service in which we're able to parallelize and scale out the log application process. Again, that same log application which used to live in the database tier is now distributed and scaled out in the storage service itself. Among other things, this allows the storage service to generate database blocks on demand, and also in the background to continuously materialize database blocks. So in this architecture, if a database node needs a block that's not in its buffer cache, it goes to the storage tier and fetches the block from there, where the storage tier can generate the block on demand if it's not already materialized. From the database perspective, this means the log really is the database. How and where the blocks are materialized are no longer all that relevant to the database. Now, because of this architecture, we're only writing individual diffs or individual deltas. and we end up writing almost an order of magnitude less data on the wire. And that's one of the fundamental innovations that leads to the high performance of Aurora. Even though we're writing less data, we're writing it to 6 different locations, which gives Aurora additional high availability and durability. So we'll talk next about how you get high availability in Aurora. So how do we build Aurora for high availability and high durability? Well, in the cloud, when you're operating infrastructure at scale, you're going to have continuous independent failures. And you can think of that sort of like constant background radiation. Things are failing, nodes are failing, switches are failing, etc. And the only way you can get resiliency and high availability is by replicating storage. And in Aurora, we actually replicate each data item 6 ways. Now you might ask, is that overkill? I mean, one common straw man in some systems use is to replicate data 3 ways. 1 copy per availability zone, for example. In Aurora, as we've already discussed, we replicate data 6 ways with 2 copies per AZ, but it's perhaps tempting to ask, can we do it easier with just 1 copy per AZ? So I'm going to take you through why we think that isn't good enough and why we replicate data 6 ways and why that's critical for high availability. As I said, we're now considering an alternative to Aurora, where you might want to replicate just 1 copy of your data to each of 3 AZs. So let's talk about failures. If you lose an entire AZ, and this can happen because you have a power or network outage or some problem with a particular data center, then if you have 3 copies with 1 copy in each AZ, and you lost an AZ, well, on the face of it, it sounds okay. You've lost 1 node. You still have 2 out of 3 nodes. You can still establish your 2 out of 3 quorum, and you haven't lost data. So at this point, this approach might sound reasonable. But if you have a failure and you lose an AZ, it's not like the gods of the cloud are going to smile down on us and give you a break and stop the background radiation of other components failing in other AZs. And after losing an AZ, you might very soon lose an additional node. So the interesting question is what happens if an additional node is also lost while you've lost an AZ? Just because you've lost an AZ, it doesn't mean that magically the background radiation stops. The normal failure model is still in effect. Things are still failing in the other AZs. So while you might think you only lost the nodes in one AZ, you've opened yourself up to the world of correlated failures, where you've lost an AZ and you've lost 1 additional node. And if this happens, recall we're talking about our straw man with 3 copies across 3 AZs. If you lose an AZ and you lose an additional node, all of a sudden you've actually lost 2 out of 3 nodes. You lose your quorum and you can lose data. And so we argue that to build a truly available system, you need to worry about not just the background radiation and not just the catastrophic event of losing an AZ or a data center, which can happen because of a power event or some such thing. You actually have to think about what happens when they both happen together. And we think of that as the AZ plus 1 failure model. Now, actually, the loss of a data center or an AZ can actually accelerate some of these other failures because of additional load that's being sent to the surviving availability zones, what we sometimes call the thundering herd problem. But if you've built your system to handle the AZ plus 1 failure case, it's easier to also handle the thundering herd problem. So now let's talk about how Aurora tolerates AZ plus 1. As I said earlier, Aurora copies data 6 ways with 2 copies per AZ, and we use a write quorum of 4 out of 6 and a read quorum of 3 out of 6. This read quorum is only used for repair processing when there's actually a storage failure. Now we can ask 2 questions. First, what if there's an AZ failure? What if you lost a data center or a power event? Well, we still have 4 out of 6 nodes. You can maintain write availability. You have not lost quorum. Everything is fine. You can lose a complete data center and everything is still humming along just fine. But now you can ask, what happens if you lose an AZ and an additional node? and now you're in the world of an AZ+1 failure. Well, let's walk through what happens in this scenario. Well, first, if you lost an AZ and you've lost another node, you still have 3 nodes. That is enough to establish a read or a repair quorum. What this really means is that you haven't lost data. You have at this point lost the ability to write data because you need 4 out of 6 nodes to maintain your write quorum, but you've not actually lost any data. What it means is that the storage service can immediately detect that you have an additional node that failed and rebuild that failed node, which is just a matter of copying data from one place to another. So you can go from the situation in which you've lost write availability but not read and quickly recover by rebuilding the lost node and restoring write availability. And if you're able to do this in the background all the time on a continuous basis, right when you've lost an individual node or right when you've lost an AZ, you can actually tolerate AZ+1 failures without losing data. And that's what lets us build a highly available, highly resilient system. One additional key point, the 3 out of 6 quorum for reads is used for repairing failures. Normal reads only need to come from a single node at a time. We keep track of which of the 6 nodes is the most performant with the lowest latency, because read quorums are expensive and can impact performance. And in general, quorum-based replication systems often suffer from read amplification of the read quorum. And unlike in the write path, any slowdown in the read path can have a big impact on performance. And so the way this works is we keep track of the progress all 6 nodes in the replica group have made, and that state is maintained and makes it easy to rebuild after a failure. And it can be used so that we don't actually need to make quorum reads. In normal read scenarios, you just read off of any individual node, generally the fastest one, to satisfy a given request. Now, it's useful to ask the question as to whether even 4 out of 6 quorum is enough for AZ+1 failure scenarios. Because what if AZ+1 becomes AZ+2, i.e. a double fault scenario, in which a second node fails before the first node failure has been repaired? So the probability of an AZ+2 failure happening is a function of the MTTF, the mean time to failure for all the components involved. And while we do everything we can, you can only reduce the MTTF, which is effectively the background radiation. You can only reduce the MTTF so much. And so in addition to doing everything we can to reduce that, we continually are working on reducing the MTTR interval, the mean time to repair, to reduce the probability of an AZ+2 failure. And so, we focus a lot of our efforts on ensuring that you never see AZ+2 failure because we fix the AZ+1 failures fast enough. So what we covered so far is how Aurora is a highly available, high performance, highly durable system, and it's very tolerant to transient issues. It's tolerant to more drastic situations, like the loss of an entire data center due to events like a flood, a snowstorm, a loss of power, etc. But sometimes you have more dramatic events. You could have a natural disaster where you've lost availability of an entire region. Now, while this has never happened at AWS, we believe it's very important for modern businesses to think about a multi-region infrastructure for business continuity. And so what we're going to cover now is how Aurora provides the ability to build global databases with a global footprint in our global infrastructure in order to implement disaster recovery and business continuity. So let's talk about how Aurora Global Database does that, how it enables faster disaster recovery and enhanced data locality to address some of these problems I've talked about, where you have a natural disaster or a region level availability issue. Now, the way Aurora Global Database works, it distributes data and replicates data across multiple different regions to allow for remote read replicas that can be promoted quickly for faster data disaster recovery, but also that bring data closer to where your customer applications live. to enable them to operate with lower latency so that you can actually distribute your entire application infrastructure with reads in many different regions. But let's start with the first goal, fast cross-region disaster recovery. The idea here is to have a distributed deployment across a global footprint where you have very fast recovery, less than 1 minute RTO to accept full read and write workloads in the event that you have unavailability of your primary region. The RTO, or recovery time objective, is critical for many businesses. They need to be able to pick up business from where they left off and not have any significant disruption to their business, even though there was some catastrophic event that may have impacted the original region. Now, low RTO is great, but that's not our only goal. We want to have global reads with very low replication latencies as well. So another goal is to have low remote read replica lag of less than 1 second for cross-continent, cross-country deployment scenarios, even under heavy load, which will allow customers to achieve very low RPO, or recovery point objectives, with the read replicas in the secondary regions lagging at most a few seconds behind the primary region. Now, low RPO is important because even if you're quickly able to resume transactions on your database with the low RTO provided by Global Database, Aurora Global Database, if your data is minutes or hours or days out of sync, it doesn't help you that much to be back up and running quickly. With the replica lag being very low, it allows you to continue your business with minimal impact. So let's talk about how it all works under the covers. To set the stage, we already talked about how in Aurora, writers are sending redo log records, or these deltas, to storage. So an Aurora cluster, even in a single region, can have up to 15 read replica instances. These readers also consume that same log stream that is sent to the storage nodes. They consume these log streams in order to keep their local buffer caches consistent and close to the actual writer. And in practice, we see in-region replica lag of typically no more than 20 milliseconds. Now, the way Aurora Global Database works, in the storage layer, we have an additional component for outbound replication in the primary or source region. And in the secondary or target region, there's a corresponding inbound replication component. These sets of agents, which are individual microservices in our architecture, are continuously communicating, where the outbound replication agent receives the same log stream that all the readers inside the primary region are receiving and sends that log stream across regions to the inbound replication agent in the secondary region. And this entire process has been engineered by us to operate in a WAN environment across the continent, across the ocean, around the world, while still maintaining high throughput. And that's the key, to be able to hit 200,000 writes per second with negligible performance impact while still maintaining low RPO across continents. Our goal with Aurora has always been to provide high throughput, high performance without sacrificing availability and durability. And what we're doing with Aurora Global Database is keeping to that same goal while increasing availability and resilience beyond a single region to a global infrastructure. So let's look at how that goal actually translates in practice. In describing the architecture, I talked about how the redo log records, the deltas, are sent across a wide area. This is typically called physical replication, because what we're actually sending are the changes to the underlying data blocks in your actual database. There's another way to replicate data called logical replication. In logical replication, what you're sending are not changes to underlying physical data blocks, but logical statements, changes to rows, maybe SQL statements. So when you use logical replication, you'll find typically that it's very difficult to sustain high throughput and low latency. And what we're showing here on this slide are the results of an experiment, where on the left-hand side, you have logical replication, and on the right-hand side, you have physical replication. And what you'll see is the blue line is the replica lag, and the orange line is the QPS, the write queries per second. In the case of logical replication, as you can see, it's very hard to sustain write QPS beyond 40 to 45,000 per second. And once you even get close to 45,000 writes per second, you see the lag start spiking. In fact, the lag goes to minutes, maybe even 5 minutes or 10 minutes. On the right-hand side, you see the physical replication approach used by Aurora Global Database. And again, we show the lag with the blue line and the write QPS with the orange line. Here you can see that we can steadily increase the write QPS and go all the way to 200,000 writes per second, while the replica lag is still under 1 second, even across the US. So a key point when you look at these two graphs side by side is that the scale of the lag on the left is 2 to 3 orders of magnitude bigger. On the left, the lag is several hundred seconds, whereas on the right, the lag is fractions of a second. So it's a much bigger difference even than your eye tells you when you just visually compare these two graphs. But what's really important to understand when looking at Aurora Global Database is how things work when there are failures. That's part of what we built it for, is to help you tolerate regional outages. But let's first start with failover within a single region. So when you're running Aurora within a single region, you'll have an application with writers and readers, and the part of the app that's actually executing transactions that modify the database is normally pointing to the writer or cluster endpoint in your Aurora cluster. And the reads are typically balanced across multiple readers, multiple read instances in the cluster. This is a very common configuration in Aurora. Many customers are using it with this pattern. Now, when you have a failover, maybe due to a transient issue, a network issue, for whatever reason, the system will choose to promote one of the readers to be the new writer. And what actually happens is there's a change, a DNS change for the cluster endpoint. And the writer endpoint ends up pointed to the newly promoted writer. And the old writer, which is now demoted to being a reader, joins the reader endpoint. Now, from the application perspective, there's not much impact. There's a small blip, and with the magic of DNS, everything proceeds as normal. But when you think about a global database, we have a different architecture. Now you have to worry about multiple application stacks. Customers typically operate in one of two modes: a pilot-light mode, in which the customer maintains a minimum set of resources in another region that's ready to come to life in the event of needing disaster recovery. And the other mode is focused on data locality, in which the customer might want to maintain a copy of their data in a second region that's closer to some of their end users or customers to provide lower latency. And so this slide shows the second model we just described, with the secondary region providing low latency read access for users closer to region 2. It's important to note that the database is operating in 2 regions in this example, and the app stack, the application stack, also exists in both regions. Here, when you have a catastrophic event, we're going to show what needs to happen in the application in order to leverage the Aurora Global Database infrastructure. So let's walk through what happens when you have a failure in region 1. So the application stack can be spun up in the event of a regional failure if running in pilot-light mode, or if the application stack is already available because it's in use for reads. Once one of the readers in the secondary region has been promoted to be the writer, then at the application level, something must be done to promote the application components to start taking writes and to start sending transactional writes to the newly promoted writer. Once that's done, the clients that are connecting to the application through some type of DNS redirection can start pointing to the new stack that is running in the new region. And now, the database portion of this process, of course, as we discussed earlier, can be completed in less than a minute from the time the primary region fails. So the database writer, the new writer that's been promoted from a reader in that secondary region, in region 2, will become available in less than a minute in most cases. So I want to talk about a couple of newer features we recently added to Aurora Global Database. The first one is called Managed RPO, or Managed Recovery Point Objective. Now, we've initially launched Managed RPO with Aurora Postgres, with Aurora Postgres Global Database. And it's designed to let you control how far behind you're willing to let your secondary databases lag from your primary database. In this example, the rds.globalDB_RPO parameter is set by the customer to 20 seconds, and the two secondary databases are lagging by 2 and 1 second respectively, so everything's fine, and managed RPO hasn't kicked in. I should point out that the metric you're seeing here, RPO lag in MSEC, or RPO lag in milliseconds, is one of the metrics that's available in Global Database that lets you track how your replicas, your secondaries, are doing relative to your primary. So everything's fine right now. Customer set the target to 20 seconds, and the secondaries are well within that 20-second target. But as we move forward in time, things have changed, and both the secondary databases are starting to lag. The Region 2 database is 30 seconds behind, and the Region 3 database is 21 seconds behind. Both are outside the 20-second limit set by the customer. So what happens next? What does managed RPO do in this scenario? Well, what happens is managed RPO controls this situation by blocking transactions from committing on the primary database until at least one of the secondary databases catches up enough to be inside the 20-second target. This means that queries and reports can continue, so you can keep reading from your databases actually, any of the copies, but any attempt to make changes, to insert, update, delete, etc., any attempt to make changes will be paused. Now, if you look at this picture, I intentionally put two secondary databases in this picture because customers who want to use managed RPO, we are recommending they have at least two secondaries, just in case something's happening in one of the secondaries to cause it to fall behind, too far behind. They don't want the managed RPO feature to kick in unnecessarily. So we always recommend that you have at least two secondary regions to protect against something going sideways in one of the regions. And so that's why in this example, you'll see I'm using two secondaries. Now, when at least one of those secondary databases catches back up to be inside the 20-second window, then managed RPO will allow transactions to start processing again on the primary database. Managed RPO is currently available for Aurora Postgres, and the primary driver for this feature initially has been financial services customers who have strictly regulated workloads in which they need to ensure that they minimize data loss below a specified amount of data in the event of a regional outage or regional failover event. And so that's what the initial driver for this feature was, but we're seeing other interesting use cases from customers in other industries now that we've actually launched this feature. So I'm going to hand it over to Steve Abraham now to talk about the other feature we recently launched for Aurora Global Database called write forwarding.
Thanks, Kevin. So we're going to go ahead and move forward into the next iteration of Aurora Global Database, which would be write forwarding. So as Kevin has already talked with you, today the ability to have multiple replicas around the world that provide very low latency and can still accommodate very high throughput, that's already there. But we've had a number of customers that have come to us and said, we really need this ability to, at least on occasion, do some sort of write forwarding from these regions. And today, we have to set it up with our own VPN or other network configurations, and it's a lot of undifferentiated lifting for us. So we really value what our customers have to say about this, and we took it as our next goal, which was to create read replica write forwarding. So in this scenario, if we're looking at this map, you can see that we actually have our main cluster in Virginia, and we have a reader that's out in US West 2. We have a reader in EU West 1, and then another one out in Australia as well. And so in this scenario, all of the writes that happen on that Virginia cluster are replicated out, obviously, to the other readers. But you can see that in Ireland, we're actually also writing to the readers that are being replicated back to that writer. So let's go ahead and take a look at how this works in a more detailed picture. In this particular picture, what we're looking at is our primary region is in Ohio. And in Ohio, we have a primary and a couple of readers. And in the application, which we're for this case calling App A, is writing to that cluster as you would normally expect and reading from the replicas. And so we also have replicas, global replicas around the world. We have one in Oregon, one in Northern Virginia, and another one in Ireland. And in this scenario, the replicas that are in Northern Virginia and Ireland, we don't really have a need to write to those. We could enable that, but in this scenario, we're just reading from them. They are just low latency global replicas on the other side of the world from our primary region here in Ohio. However, in Oregon, we do occasionally need to write, and we're looking at what we're calling App B here, is writing to one of the readers. And what happens here is that that statement, the actual statement that is issued to that reader, is forwarded back to Ohio, back to the original writer in the original primary cluster. And that write happens on that writer. It happens to the storage, just as though it came from App A. And once that change is written to that storage, then that change is streamed out to all three of these global replicas, the ones that are readers only, and the one that is also occasionally taking writes out in Oregon. And so at that point, then all of the readers can read from their respective storage nodes. So there's no need to go back to the Ohio region in order to read your reads. So by sending all of the writes back to the primary region to that single writer, we're able to make sure that it simplifies the application so that all of the writes are going through that single funnel and allow you to maintain transactional consistency, even though you have writes coming in from potentially multiple different reader regions. Once all of these writes happen and they're replicated out, obviously, like Kevin was mentioning earlier, you can promote any one of these readers into your primary if you needed to fail over for some reason or otherwise. So since we've laid out kind of how write forwarding works, let's go ahead and move forward into a demo, and we'll see more of a hands-on approach to global database. So right here, what I'm going to do is click on the databases link, and I'm going to create a new cluster. In this case, you can see in the upper right-hand corner, I'm in the Oregon region. And so we're going to go ahead and do the standard create. We're going to use the Amazon Aurora engine type. We're going to use Aurora with MySQL compatibility. And we want to make sure that we select the latest version, 2.08.1, which enables write forwarding. For our purposes here, we can just do dev test. And then we'll scroll down. We'll name our Oregon cluster. We'll just name it Oregon cluster. We're going to go ahead, use admin, auto-generate a password, a secure password. We'll retrieve that later. An R5 large, that should be adequate for our purposes here. We don't need to create an additional replica in the region right now. We'll use our default networking connectivity. And essentially, for the most part, they're just defaults for the rest of this cluster creation. Create the database. Then we need to wait for just a minute here. Now you can see at the top, there is a button that says View Credential Details. We click on that and go ahead and copy our master password. And we'll set that aside for later use. You can close that banner out and then give us a little more screen real estate here. So we can see the cluster and the instance in Oregon, they're still creating. We'll give it just a second. The cluster is online, give it another second. We now have the cluster and the instance both online together. So now that they're both online, it's really easy to just go to Actions and say add a region. So let's go ahead and create a region in Ireland. We're gonna first create the global database and we'll name it Global DB. We'll select Ireland for our secondary region. We'll use the same size instance. We don't need a replica in that region. We're going to use the default for the connectivity. You can see we don't really have to change much, except we want to make sure we enable read replica write forwarding. We'll add that region. And then you'll see that once we add that region, we now have something of a hierarchy here where global database is really a container for both the Oregon cluster and what is now being called the global DB cluster 1. We could have named that anything we wanted, but we'll stick with that. So now we have two console windows. The one on the left is connected to Oregon. The one on the right is connected to Ireland. And so let's run a few commands and see how this works. First thing I need to do is create a database. We'll call it testDB in Oregon. And then we're going to go ahead and set that as our default database. And we'll create a table. All of the DDL statements need to happen in the primary region. So in this case, that means we need to create the database, create the tables, etc., inside the Oregon region. We'll create this simple table that has just a row ID and then a single string column. And we're going to insert a single row into this table. And we just want to say, essentially we're going to say here that it's hello from Oregon, right? Because we're doing this from Oregon, and we'll know where this record came from. And so there we go. Happened very quickly, of course. Let's go ahead and select the rows out just to make sure that we can see what's inside that table. Of course, hello from Oregon. Now, when we flip over to the Ireland cluster, show databases, you can see that the testDB was created automatically. We'll go ahead and change our database context to testDB. Let's go ahead and see if that record was replicated out, which is global database. There it is, hello from Oregon. So it's out there. So now what we want to do is we want to insert a record on the Ireland side. So the first thing we need to do here is set the Aurora replica read consistency setting. This has to be set. There's no default for it. And so we'll just use eventual for this purpose. We'll talk more about that later. So now that we've set that, now you can see I can actually type an actual insert statement in the Ireland region, and it's going to look very much like the one that I did in Oregon. The main difference here being we're going to just say hello from Ireland. And we'll go ahead and insert that. 0.12 seconds, so very quick. We'll select from test table and we see it's there. And then again, we'll double check in Oregon to make sure it made it there, and it did. So now what I've done is I've spun up in the background a sysbench workload that is pushing the Oregon instance right here. You can see that under CPU, we're at 96% on the right. Let's go ahead and drill in on some of these metrics in the console. So again, looking at the CPU, it's very high. We're really kind of redlining the CPU. It's a hefty workload. We have 250 connections that are currently connected to the Oregon cluster. And then if we scroll down here, let's take a look at what the actual workload is doing. It's an insert only workload. And right now we're pushing through around 10,000 commits per second. So about 10,000 inserts per second. The average commit latency, it varies between 15 with a peak of around 25 milliseconds. This is all local within the Oregon region. So this is, about what we would expect. It's fairly normal for, pushing an instance that size. So we're going to take a look at what's happening in Ireland. And this will give you an idea about how you can keep an eye on managing your global database and its performance. So when I scroll down here, I click on monitoring in the Ireland region. You can see the CPU utilization is very low. There's not really much happening there. In fact, if you look over to the database connections over here, you can see we had one connection. That was me actually connecting a while ago, but we're back down to 0 because we're not actually talking to the compute node. We're writing storage to storage. But you can see here that the replicated write IO is at around 400,000 because we're still performing writes. The writes are just coming from the storage layer itself. It's not coming from the compute node. Same thing for the global database data transfer in bytes. You can see we have a very steady load as we would expect from our steady state workload that we're pushing. And our replication lag, this is a key metric here. You can see even though we're redlining in Oregon, we're around 75 to about, we'll call it 85 milliseconds of latency in Ireland. So it's not bad writing all the way around the world from Oregon to Ireland. You can see that the volume is increasing in size. Our read IOPS, of course, are low, as we would expect. Again, the volume write IOPS, which match the replicated write IOPS, again, are at about 400,000, as we would expect. So while this workload is running, let's go ahead and log in Ireland. And we're going to change our database to Sysbench, and we're going to go ahead and we're going to try out the different Aurora replica read consistency settings. We'll start first by looking at eventual. So we'll set eventual, and then we're going to just do a select count star from one of the Sysbench tables, which we know is currently under load. You can see that that executed very quickly. We're talking 400ths, 200ths of a second. Let's switch it up now to session. Now, we're not really writing anything in our session, so again, we expect this to happen very quickly, and it does. We're 200ths, 500ths, very quick. Now we're going to switch it over to global, and global waits for everything to be settled before it comes back. And so it's still, you'll see, very performant, but we're at 5900ths, 5000ths, a half a second. We're at right around about a half a second for each one of those selects. But it is a transactionally consistent view of the data. So best practice around this would be, if you're okay with having your data be a little bit on the stale side, we're talking, based on this particular example, 75, 85 milliseconds behind. If that's okay, then you'll get better performance reading using the eventual consistency level. Session level, you can use that if you know that you have other things happening within your session. But if you require an absolute read after write, then I would suggest that you use the global consistency level. And so it will take a little bit longer, but if that's necessary for your application, then that's what we want to do. So with that, let's move on to the Aurora Global Database 2020 roadmap. So the first thing is, anywhere we have Aurora, we have Aurora Global Database. That is available now. Aurora Global Database is available everywhere. Up to 5 secondary regions. We launched initially with only 1 secondary region, but now you can have up to 5, which gives customers a lot of flexibility. And with write forwarding in those, you can also forward writes from those different regions. We launched, MySQL 5.7 compatibility this year as well as Postgres 10 and 11, with Postgres 12 support coming very soon. Another thing that is a really big win for customers is we initially launched Aurora Global Database using the global database mode. And so you had to create a cluster in the global database mode. We've actually gotten rid of that. So if you are in Aurora today, all you have to do is just what I did in the demo and select add a region to your given cluster. And so that would be the in-place conversion from a non-global database to a global database. And then the last thing here that we have coming up soon is managed failover and fallback. And what this is this just allows you to, let's say you want to just test between two, let's say you have 2 regions and you want to, switch over from one to the other and then back, just because maybe you have compliance reasons, maybe you have standard drills that you need to run within your organization to make sure that you are able to fail over and fail back. And this will allow you to do that in a more automated and easier way. I'd like to thank everybody for your time today, and we'll open it up to questions. Thank you.